What's up guys, this is Milos. Welcome back to my channel. In today's tutorial, I will show you how you can leverage the awesome KrigR package in R to download Era 5 climate data, do some kriging interpolation, and then create some very crisp time-lapse and static maps for different temperature variables. Welcome back to R, where we start our data visualization adventure by first of all installing the amazing KrigR package, which is going to help us get the Era 5 data in no time, and then after that also perform kriging operation. So we'll be installing this package from the GitHub, and to install that you first of all need to have a package which is called DevTools. Now from DevTools, we will be using one specific function, which is called install GitHub, right? So we're gonna pass to this one the link then to this GitHub repo. So this is where the KrigR is. And then after that, you just need to run this and then start the process. Then we can proceed with installing and loading other packages that we will be using today's tutorial. And if you don't already have, I strongly suggest that you install package pacman, which is gonna help us install and load the packages in no time. So one thing that you need to do here after installing pacman is to call this pload function, which essentially what it does is it searches through your library, then it sees if you have already installed the packages that you want. If you don't have, then it installs it for you, and then it also loads for you in this session. So it's a pretty awesome one. Okay, so you already installed KrigR, so simply we can just load it here. That's the first one that we'll be using for getting Era 5 data and then also kriging it. The second package we need is called rGeoboundary. So this one is going to help you get the polygons of countries and also subnational regions for this analysis. In this tutorial specifically, we'll be using country polygons, but I will also show you how you can get subnational polygons, so of regions. The third package, and extremely important here, is the Terra package, because the Era 5 data will be returned in the raster format. So ANSI will also be working with TIFF format. Terra will help us actually then perform some operations on these files. Then the next one, of course, will be using tidyverse. It's actually an umbrella package for data wrangling and data visualization. From this one, we will definitely be using dplyr and also ggplot2 for mapping. Then after this, there is one more that I'm going to be using, and that is gganimate, which is used for animation. So that's right, we'll be also creating animated or time-lapse maps, and gganimate is going to help us do that. All right, before we move on, I just wanted to share with you here the packages and the versions that I will be using here, along, of course, with the R version. All right, we have all the packages installed and loaded into R, and then the next step is to choose our area of interest. And to do that, we will use rGeoboundaries package for fetching simply national boundaries. So if I actually now try to select the functions, you will see here that it has a bunch of this gb_adm functions. So in essence, it has 6 of them. The first one is it's going to give you just national boundaries, and this is what we're going to go for. But essentially here, you can also choose some other levels. So other subnational levels. So if you want to filter out maybe a lower level of analysis, perhaps you can also use that. Now, the important thing is whatever you choose here, and I'm going to choose again this one, you need to specify what is your country or countries of interest. So we'll be working today on the area of Switzerland, and over here you need to then place ISO3 code of Switzerland. And for Switzerland, this is CHE. For some other countries, please do Google that and check. Now, what we're going to do is assign this to an object called country SF, and there you go. Package KrigR consumes climate data from the climate data store. And in order for us to use that, we first of all need to register for free with this data service. If you already don't have an account with CDS, I will show you here how you can get one. So we first of all head to the Climate Data Store website, the main page, which is cds.climate.copernicus.eu. Don't worry, I will provide this link in the description box of this tutorial. Now, once you are here, you want to head to the upper right corner of the screen where you will see this login-register. If you click on this, there's going to be a new window asking you to do something weird, which is actually to create an account with the European Center for Medium Range Weather Forecasts, because this institute is essentially the one that is feeding this climate data store. So you need to click here on I understand. And then this is going to take you actually to the ECMWF website. Now, I already do have an account here, but nevertheless, I'm going to register so I can show you how this process works. So you need to click here on register. And then over here, what you need to do is you need to provide your first and last name together with email. And of course, you need to choose your password. And after that, to just confirm that you're not a machine, but a human, you also need to fill out the CAPTCHA here following this example. You can also check the terms and conditions after that, and then you can click on register. Once you fill out your details and click on the register button, you will be redirected to a new window that is going to ask you to head back to the email address you used for the registration and then activate your account through the email that you got. If you haven't received the verification code in your email, or you haven't received email at all, while you're still at this page, you can just click on this link here and this will hopefully resend the email. If you ever did receive the verification code in your email and you manage to activate your account through the email, what you can do next is simply click in this upper left corner of your screen. You can click on this ECMWF, and then this is going to redirect you to the main page. On this main page, you want to go to the login button in the upper right corner of your screen. And then this is going to take you to the login page. So here you just need to put your email that you use for registration and verification, and also your password, and you can click on login button. Now, as you click on the login, it's gonna return you back to this main page. But then if you go back to this upper right corner where you clicked on login previously, now you will see your name here. You should then head back to the Climate Data Store website, which is at cds.climate.copernicus.eu. And then you should again go back to the upper right corner of the screen where you have login register. This time, however, once you click on this, you will notice your name. So you successfully logged in because now you also have fulfilled the main requirement, which is having also account with ECMWF. What you want to do is hover over your name and then click on this Your Profile option in this main menu. And this is then going to take you to your main profile page at CDS. Congratulations, so you successfully logged in. Now, what you can see here is first of all your personal information. So you can see your first, last name that you use for registration, your email, and your password. Now, what is very important is remember your email, or actually copy your email, because in the next step, that is one of the things that we'll be using. Now, if you scroll down a bit, so you are still on the same page, but scroll down a bit, you will see this field which is called personal access token. This is essentially your token, your password that we also need back in R. Also, we need to provide this to KrigR so that the communication with the CDS does not fail for you. So please, again, also copy this one. So these are the two pieces of information, again, that you need. The first one is your email that you use to register to this service. And the second one is this personal access token. So in this video, I black it out because, I don't want you to see my personal access token, but you will have your own. So with these two pieces of information, your email and personal access token, we're now ready to go back to R and fetch the data using KrigR package. After you successfully register your account and got your credentials, we are now ready to go back to R and then issue a call for a specific data extent. So before we do that, however, we need to actually, first of all, define two things here. The first one is your email address, which you use to, of course, register yourself. So over here, you should define that. So something like this, you will have it here and you can define it here. But remember, it needs to be under double quotation marks because it needs to be passed as a string. The second thing you will do here is you will tag that API key and again, put it here under double quotation marks. I'm just putting here asterisk because I will be using mine. I don't want to reveal it. But in your case, again, for the API user, please use an email. And for this one, use, of course, the API key that I showed you in the previous step. Okay, so once you actually have that, we can go ahead and a bit inspect what are the data sets that this package KrigR supports. What are the data sets that we can get from CDS. So to do that, we start off with the first function, which is called meta list. And I'm just actually going to put here KrigR so that you know that it actually comes from KrigR, this one. All right, so once you actually run this list, what you will see is a list of data sets that you can fetch. So there are actually three data sets here. The first one is the reanalysis era 5 land monthly means. So these are average monthly values for a specific variable of interest, and we'll be using today this one. Right, so we're not going to make it that complicated. The other two, reanalysis era 5 land and reanalysis era 5 single levels, these operate on hourly levels. So they are way more granular, they are way more complex, and they take way more time to get them. If your specific analysis requires using these two data sets, you can proceed using this tutorial, of course. It just keep in mind it's going to take way more time. For the simplicity case or sake, I'm going to use this first one because it's already on the monthly level, which we will need. Okay, so once you have that, once you know, okay, these are the three data sets, the next thing is I want to check what are all the variables that are within this, specific data set. So to do that, what you can do is you can use, again, from KrigR, another very convenient function for fetching metadata, and it's called meta.variables, this one. Now, if I actually run this, it's going to give me the huge list and I won't see anything. What instead you can do, and what I like to do, is pass this creates a data frame. So something like this. And then once you do that, you can go ahead and inspect this data set using, for example, this fix, and then pass this here, this name vars_df. So what you will essentially see here are several things. First of all, the variable name and then the CDS name, which sometimes they don't really, overlap. What you're interested here is this second column, which is called CDS name. This is the one that will be passing. And we will specifically be working here with 2 meter surface temperature. So this one. And over here in the description, which is the third column, you can see the description of this variable. So temperature of air at 2 meters above the surface of land, sea, or in inland waters. But in our case, it's going to give us only for the land. And then here it says how it's calculated. Since it's going to return us a raster, it's essentially, this is already interpolated. So it's interpolated between different points from which they were taking values. And then the fourth one is very important. It tells you what is the unit. You can see here it's K, so it's not C for Celsius. K is for Kelvin. And what we need to do is we will need to actually transfer from Kelvins to Celsius so that you actually understand what it means. But I will show you that in a bit. Now, one thing I forgot actually to tell you here is you can also pass within this meta variables function, you can also pass the name of the data set, and perhaps this is even better. So what I did here is I just passed here the name of the data set that we'll be using, and then you will get the list of the variables only for this data set. Currently, that's a list of 50 variables. So once you actually know this, you can also then understand a bit more about the data set itself. So there is a third very convenient metadata function from KrigR, which is called, again, meta.quickfacts. And again, here you can pass the name of this data set that we will be using. And once you pass that, you can simply run this and then you will get information. So let me actually just pull up this so that you can see what actually is going on after we pass this. Essentially, you will get information about this data set, several things. So I'm just going to go back to this one. First of all, the name of the data set, which you already know. Then you will see the type. Now, why is this important, all this? Because all this information you will be passing actually to KrigR. The next step will be downloading this data. And KrigR is going to ask you about these things. It's going to ask you what is the name of your data set. So it's this one. Then what is the type? We'll be using the first one, simply monthly average reanalysis. Then you have here again a short description of this data set that comes actually from the CDS website. So you can check it out, what it means if you're not yet familiar with Era 5 land data set. Then over here, it's going to tell you what we already know, that the resolution is monthly resolution. Of course, you can also aggregate this to the year resolution within KrigR, and that's what one of the things that makes it awesome. T-step here is actually, it means how many of these resolutions are you going to get. So if you, for example, if you put here T-step 1, it means I want to get every month in a year. So it's going to return you, let's say you take for 1 year, it's going to return you the data for all the 12 months. If you select 2, it's going to return bi-monthly data, 3 monthly, and etc. T-start, this tells you, okay, when does the data start? So it starts on 1st of January 1950 at 1 a.m., meaning simply, it starts simply from the year of 1950. It has information for the entire year of 1950, all the way to present date, with a lag of 3 months, it says here. So it's very important. Now, we will be using only data for the fullest year, and that's, in our case, will be 2023. So we're not going to go into 2024. Very important, the projection is WGS84. So it's simply a standard projection. Spatial resolution, also interesting, it's 0.1 degrees. And we'll be using kriging function here in R, also as a part of this KrigR package, which is going to actually help us to make this resolution even crisper. So we're going to move it down to 0.01 and make it much, much crisper. So this is not that crisp resolution if you're working with the country size of Switzerland and the data for Switzerland. So that's going to be pretty pixelized. So we're going to fix that. Then it tells you here what is the area. So this is simply the Earth area. As you can see, it goes from minus 180 to 180 degrees longitude and minus 90 to 90 degrees latitude. And the final one tells you what is the actual format in which you will be fetching this data, and that is netcdf. Now, this was a very lengthy intro into this dataset, but I did it for a good reason, because in the next step, we need to provide information to KrigR, which is then gonna download the data for us. And then the first thing I want to define here with you is what is our start date. So for the purpose of this tutorial, I'm not going to go wild. I'm going to get, well, some would actually think I go wild because we're going to be taking here data for the last 10 years. So the temperature data, 2 meter surface data. So we're going to start from 2014, 1st of January. So you're going to write like this, and then you're going to make here a space. And what is important, you need to put here the hours and the minutes. And because we're starting from the very, very beginning of the 1st of January 2014, you do want to put here that you're starting from, you're starting here from the midnight, right? So the very first hour of that. So that's the only thing you need to do. Now, the second thing is you will define also here the end dates. Again, as I said, we'll be here working with the last 10 years. So we're going to stop at the 31st of December, 2023. And again, here you need to specify actually 24, meaning, this is the last day and the last hour of this year. So what is this going to give us? It's going to give us all the months starting from 2014 and ending with 2023, which means 120 months, right? So 10 years times 12 months, 120 20 layers. When I say layers, it means this following function is going to return to us a single raster file, but it's going to have 120 layers. Okay, the second thing we're going to do here, and probably the most important, is we need to define first the object where we're going to save actually this. So the data will be saved locally because we will tell KrigR to save locally, but it's also going to be stored in this temperature raw object in R. Now, there is a new function now, which is called cdownloads. It's different from the previous tutorial where I was explaining how to download the data using KrigR. So this thing has changed now because there is a new API. And then we can go ahead and then define in a similar fashion like we did in that previous tutorial. So the first thing we want to define here is what is the type. And if you remember it from the previous part, the type is actually simply the, what is the data set that we want here. I think this is actually the wrong one. So the one that we want here is the type. So the type is the general type. So monthly average reanalysis. So that's the type. The second thing is the variable we want. And if you remember again from that list, we want 2 meters temperature above surface. So that's the one. Now comes the part when we need to define the data set. And now is the part where I actually can use finally this reanalysis error 5 lab monthly means. So this is the data set. Then we go to the next element here. So this is date start And for the date start, we already defined here, it's called start date, and date end, or date stop, actually in this case, which we also defined here. So again, the data will go from 2014 beginning to the end of 2023, the last 10 years. Okay, now, usually what you should do here is also you should define here a time zone, but you can also do it very conveniently in KrigR. And because we're fetching data for European country, I'm going to put here CET, which is Central European Time. If you are not sure what is your time zone, you can just use maybe UTM like this and write it here. Or you can just pass it, of course, here in the string. It's really up to you. What is the function, aggregation function that we're going to get here? Well, since we want to get here only a monthly level data, and it's already averaged, well, let's just take the average data from that. It doesn't make more sense to kind of get maybe maximum or some other, function. The second one is what is going to be our resolution. So remember, because we're already taking the monthly data, there are two options for us. We either go for a yearly level or we go for a monthly level. And we're going to go for a monthly level because I want to show you some tips and tricks using the monthly level. If you want to go for the annual level, you can simply write here year. The next one is the so-called T-step, and this is the one that is maybe not so intuitive. But as I said before, because we want to get data for every month, for every year, in total data for 120 months, I'm going to put here T-step equals 1. Okay, and then here you can also specify where you want the data to go. I'm just going to put it into my current working directory. And because the data is also going to be saved locally, you definitely need this file name. But remember, we're going to call it the same way we are calling also this object, so there is no confusion there. Remember, file name here, you don't need to specify the extension because the file will be already saved as the NC file. So that's totally fine, just leaving it like this. But one thing you should define here is extent. And there are two ways to define the extent of interest. So one is the one that we already have, which is simply, let's use country SF here, spatial. The other thing is if you want to have, for example, area of interest, so a bounding box. It's super easy to do that also in KrigR. What you can do is you can use Terra and then function extent, which is basically, or function ext, which is where you can define this bounding box. And then this is very important. So you need to define here your, first of all, what is your minimum longitude, followed by maximum longitude. And then you can go with minimum latitude and your maximum latitude. So actually, let me write this below. You might not be able to see it in the screen. So this would be actually the way to do it. So of course, without this pound, something like this. Again, minimum longitude, minimum latitude, and maximum latitude for your area of interest. But we're simply going to take for Switzerland, so we are fine with this. And then once you actually define this, we're almost there. There are only two things to do. One of them is providing this API user, which we already defined. And the very last one is providing this API key, which we also defined in the previous step. It took about 2 minutes for me to get this data. Of course, this is going to depend totally on, how many queries are currently at CDS, how many people are trying to also fetch the data at the same time, how fast is your internet connection as well. But eventually, as you increase, the number of years you want to analyze, this is also going to take more time. So just keep that in mind. Now, I'm here want to show you what exactly is the data we're working with here. So I just opened that one, and one of the first things that you can see is, of course, this familiar resolution that they already, tell there in the metadata. So it's 0.1 times 0.1 degrees. Then we have this extent for Switzerland. Then the coordinates reference system looks very arcane here, but essentially it is WGS 84. And then here you will see for names and time that these are our layers. So we have 120 layers, and we have the time here is also recorded. So it says here it goes from 1st of January 2014 and all the way to the 1st of December. Basically, here, this is not to indicate the date, this is simply to indicate the month. So essentially we have here the average temperature data for 120 months, going from 2014 to 2023. Sometimes when you run C downloads, you might get the following error message: permission denied, required licenses not accepted. Not all the required licenses have been accepted. Please visit, and then offers you a link to the CDS website. This simply means that you did not accept some of the licenses that CDS requires you in order to download the data from their website. So what you need to do, this link that I highlighted, you simply need to click on that link or just copy to your browser and then press enter, and it will take you to this page. So once you click on that link or open it in your browser, you will be redirected to this part, which is called terms of use, and it's on the CDS climate website. So what you need to do is you need to click on this button, which is called login register to accept licenses. As soon as you log in, you'll be redirected to the landing page, but this time you will have a button which is accept terms. You just need to click on accept terms and you are good to go. If you want to quickly inspect if you did everything right, you can also visualize in a quick and dirty way what you have, and you can use plot from Terra. So we can then pass this temperature raw, and because we have here 120 layers, you can simply take, for example, layer number 120. So this is going to give you then the data for December 2023. And this is how the temperature data for December 2023 looks for Switzerland. And as I warned you, it's pretty pixelized, but don't worry, we will fix that in one of the next steps when we'll be using kriging for the interpolation. And then you will also notice the legends because we are operating here with Kelvins and not with Celsius. Again, we will be also fixing that in one of the next steps. So to fix those pixels into a much finer resolution, we'll be using kriging, which is an interpolation between different random scatter points by using some prior covariates or variables. Now, what it means is that we now need to actually define a model, and based on that model, we will then predict the possible values for those areas that are not well predicted, so why we have actually pixelized, and then come with the final resolution. So this is the next or the second part of what this awesome KrigR package has to offer. So preparing these covariates. To do that, you can use covariate setup from KrigR. And over there, what we need to pass are two things. So what is going to be, like for every prediction, what is going to be our training data set and what is going to be our target resolution. So the training data set is no more, no less than this raw temperature data, this currently pixelized one. And then the target is what is the resolution you want to get at. Now, the current one, if you remember, is 0.1 degrees. We have Switzerland, so we can confidently go for 0.01. So we can downscale to this one. We can make it so much finer. But if you're working with some, bigger countries, perhaps you don't want to scale up, downscale to this much. Maybe you can just go for 0.05 or, something even smaller. Anyways, we are working with Switzerland, so we can afford that because it's a very small area. It's just something to keep in mind. Now, in terms of the covariates, what is really cool about KrigR is that these covariates that it's going to use for prediction and for interpolation, you can actually use some of the predefined covariates. So one of them that it uses, and you can actually see here, is soil. And also there is this one for elevation, which we are going to be using. So this GMTED 2010. And this one is going to be actually, by running this function here, KrigR is going to download this for us and prepare, and we don't need to do anything about it. So that's pretty cool. So over here, what I'm going to do is I'm going to actually define this one. So GMTED 2010. And then what I'm going to do here is I'm going to say that we don't need to keep the global one, so it can just save it locally. And then what I want to do here is I want to use TIFF file as an extension. So here you can actually choose if you want an NC or a TIFF file. This app has actually created a training and a test data sets locally. and you can check your local working directory where these were downloaded after this. And once we actually have this, we can go to the next stage, the third stage of the KrigR package, which is kriging. The interpolation of these different points using these covariates that we now have defined. Essentially, what we're going to do is we're going to, using this, of course, function, what we're going to do is we're going to predict what are actually what is the surface temperature for these other areas of Switzerland that would then give us a much finer resolution. So essentially, we're going to predict temperature where currently maybe it's not predicted well, and we're going to be using this elevation data for that. So that's in short. Now, for this, we again need to define an object where we want to store these results. And then from KrigR, we want to use a function which is called kriging. Now, within this function, you need to specify several things. The first one is what you actually want to use to apply this kriging to. And that is going to be simply our raw temperature data. The second thing you want to do is what are the training covariates? Now, the training covariates come actually from this covariates data set that we have. So if I put this $, well, it doesn't show now at the moment, but essentially, there is a training and the targets. So we're going to go and use here the training variable. And then you also need to specify here the covariates target. Again, it's going to come from this covariate ls that we defined. So we just simply need to choose here target from this data frame. Then the next thing is the equation. The equation here is what is the name of the variable that you want to use for this, prediction. And we have only one variable. So this is this elevation data, which we previously used in the previous step to prepare. So we're simply calling this, that this is the one that will be used in our equation. Okay. Then this is the number of points that you want to use for interpolation. So you can here, the default one is infinite number, so just take all the points. But I found that this is very, very resource intense and it's very slow on my machine, despite being a pretty fast machine. So what I do here, I tend to decrease here. And here I decrease to 25. You can try and play with this number, increase or decrease. Of course, the higher number is going to give you crisper resolution, but the downside is it's going to take up much more time to process this. Then here you can also define the course. Now, the good thing about this one is you can use this function, which is called parallel detect course. And this is going to tell you how many cores your CPU has. Now, mine has quite a lot, but I'm not going to use all of them. I'm going to use 10. I also found if you're using all the cores, that's quickly going to consume entire memory, and then it's going to actually abort this session. And then you have a problem because you didn't download the data. So keep this in mind as well. There are some other things here which are important, and one of them is defining, of course, the file name. So for the file name, we're just going to go ahead and use the name of the object in R that we defined. There's also the file extension. This time I went for the netcdf file because I found also in one of my tests that the T file was consuming way more memory. I don't have a good explanation for that. Then that's why I used the NC file. For this one, we can again just simply save on our working directory. And then because we chose here this netcd file, we can also compress the file that we're going to save. And 9 is the highest value of compression. So this is going to offer you the fastest result in terms of saving to your local drive. And there are two things that I can also do. For example, I don't want to keep all those files that are going to be part of this kriging. I don't want to keep them in the temporary memory of my local drive, so I'm just going to get rid of them. And one more thing I want to enable here is verbose. I want to get the messages about the process of kriging. This time it took a bit more than 2 minutes, which I find still pretty reasonable given that it was, 120 layers. So that's quite a lot, and 120 files that I had to put together. But once this process was over, we actually now got a spat raster. So we got a raster again with 120 values, but they're now much crisper. As you can see, KrigR attempted to make a resolution very similar to what we asked for. So our ask was 0.01. It gave us 0.008, so it's a bit even crisper than what we asked for, and that's totally fine. The aesthetic is the same as the old one, and these are of course the names, and you can see that it's the same, of course, date range again. You can go ahead and inspect now once again if you're curious, and I guess you're curious how this actually looks like now once we did this kriging. So you can just simply go and take this temperature kriged, and again, maybe you can take, just for the comparative purposes, you can again take layer 120 and run this and see what you get. Okay, so one thing you will notice, we actually interpolated the temperature using kriging for the entire extent of Switzerland. That means everything in the Switzerland and around Switzerland. But one thing you will also notice, that now we have a much crisper, so finer resolution of this temperature, average temperature for Switzerland, in this case December 2023. And you might notice, if you're familiar with the relief, with the terrain of Switzerland, that of course it resembles, the terrain. You can see the contours of the Alps, and this is simply because we used digital elevation model as one of the variables to predict, of course, these additional pixels, and makes this much crisper. Guys, one thing I want to also point out is that if for any reason, this session might break, you still have the file saved locally. So what you can do is, let's say, for example, you want to have the same name. What you can do is, assuming you're operating now from the same working directory where you saved that file, you can simply use here Terra of Rust. And what you can do is, you can use this temperature kriged if you saved under this name. And then if you use, I think .tif, that's what we use, right? No, we use .nc. All right. Anyways, .nc. And this is essentially gonna load this into R if you had to restart your session for any reason. As you notice, we got the temperature data for the entire extent of Switzerland, but I just want for the Switzerland proper, so only for the space within Switzerland. And now I'm actually gonna go and crop that raster file so that I get only for the borders of Switzerland. So I'm gonna go and actually create here temperature predicted. It can be also temperature cropped, whatever you desire. And then we're gonna use this temperature kriged that we previously created. And then we can use Terra crop function. So over here, we're gonna be using country SF to crop this. We're gonna snap everything that is inside of the country SF, and the rest we're gonna mask, or we're just gonna declare as a missing value. So that's why it's gonna, just disappear. And then the second thing, which is actually optional, highly depends on your context, you can also go ahead and reproject that value. Remember, we were here working with WGS84, but because this is a European country, I wanna go ahead and use a more European, coordinates reference system. So I'm going to be using EPSG 3035. If you are curious what is the one for your country, you can go and check the website, which is called epsg.io. And then over there, just type the name of your country, and you will have, in one of the options, you can see what is the suggested coordinates reference system for your country of interest. Okay, so once we actually do this, we can go ahead and check whether we indeed managed to crop this. So the cool thing that we have multiple layers is that we just need to crop a single file, and it's going to crop actually all the layers. So after cropping that, we can simply go and check, for example, maybe again, since we are working with that one, let's check that layer 120, or actually the average temperature for December 2023. This returns the temperature data only for Switzerland proper. All right, now that we have the data interpolated and in a much finer resolution, I want to show you how you can visualize temperature in 3 ways. First of all, I want to show you how you can visualize the average temperature for a specific month or every year. And in this case, we're going to be going for July. So July of every year from 2014 to 2023, how does it look like for this extent of Switzerland? The second map I will going to show you is how you can do the same, but for seasons. And here I'm going to, for example, pick summer, and I'm going to pick 3 summer months and then do the same analysis for that. Of course, this requires some data wrangling, and that's the reason why I want to show you this. I want you to learn this more complex things so that you can also apply it to your own projects. And the third one is the temperature anomaly, where we want to show actually how extreme was the year of 2023 compared to the years 2014 and 2022. Of course, this is not the perfect case. You actually want to have a much larger, their set, but you can apply what you learn here to your own project and for, of course, the wider time series. So let's start off with the first project, and that is how do you create an animated map for every July from 2014 to 2023. Seems daunting, but it's actually pretty easy because it's about defining your layer names and then subsetting only those layers that correspond to July of every year. Remember, we have 120 months here, but we want only to have at the end 10 layers. So for each year, we want to have only the July data. You can also apply this to any other month. You just need to change, of course, the number of the month. So this is what we're going to do. First of all, we're not going to define the months vector. So we want to first understand, okay, what are all the months that we have there? How do we do that? We can utilize here that start and end date that we have. But first of all, in order for R to understand that these are dates and it can extract months from them, you need to first declare here as date function. So this is going to tell R, okay, this is a date, so I can work with that. Now, once you have that, once you define here what is your end and start date, so you have a range here, you simply need to say here that you want to define here by month. So you want to have actually months at this month vector, okay? Now, once you have that, once you define this and run, I just want to show you how this looks like in our case. So this returns a vector with 120 values. And in this case, what we have is we have for every year, we have this date. Now, you might be confused that, we have the full date here. So we have not only the month and year, but we also have a day. So this is simply the way R presents this, and because we didn't really specify what is the way it would, present them, but essentially it knows that these are labels for the months, and we have here 120 months. Now, what is the next step here? The next step is having this information. We can then name our temperature predicted. We can name that using these months vector. So essentially, then this is going to give this to this one. The names are going to be now proper names and not just some numbers. And then once we have that, we can then filter July temperature for every year from 2014 to 2023 inclusive. To subset, there is a very cool function in Terra, which is also called subset. Now we're going to here subset this temperature predicted. And what we're going to do here is we're going to take this very cool function from base R, which is called grep, and we're just going to say here that look for this pattern. So look for every name that has here 07 and 01, meaning look for everything that has July in its name. If you're interested for any other month, what you need to change here is simply this first part. So instead of 07, maybe if you want for November, you can put 11 here, and that's basically it. The second here, we need to tell R where to search for this pattern. So it should search among the names of this temperature predicted that we have here. Now, once you actually have that, you can go ahead and inspect what actually this means. So, and what it means is if we run this now July temperature, you will see here that I have here only years. So I have 2014 all the way to 2023, which you cannot really see at this. But what you can see, it goes from, in terms of the time, it goes from July 2014, it goes all the way to July 2023. So it does not include anything else that is not July. So that makes it, in this case, we got actually what we needed. Now, if you're not sure if it's really, you know, got those months that you wanted, you can also check, okay, you know, what is the number of layers, or what are all the names of this July temperature? And this is actually going to tell you, because the names of the July temperature raster is also equal to the number of layers of this July temperature raster. So if I just go and actually quickly run this and go for names, I should be able to see only 10 names. And this is exactly what I see. So the names are 14, 15, 16, 17, 18, all to 2023. So this actually makes sure, indeed, we have only 10 layers. And then the next thing that we should do here, I think, is define the names, of course, in a more appropriate way. So define names as simply, you know, years. So what I would like to do here is define the range of the years, and we know the range. So the range of the years is simply 2014 to 2023. So that means that I can just use these years and then define. And from now on, the names of my July temperature are going to be years. So each name is going to be one number. To be able to work with ggplot2 and especially gganimate, we want to transform this raster file into a data frame. And that's pretty straightforward. We did it so many times before. We're going to be using as data frame and then passing here this July temperature object that we have and telling R that we want to return coordinates here. Essentially, we'll be returning 3 columns, longitude denoted by X, latitude denoted by Y, for each of the pixels, and then the third is going to be the value column, which is going to be the temperature in Kelvins. And then we're also going to remove here any missing values. Okay, so you can also quickly inspect here what this yields. Actually, it gives quite a lot, because you should not be doing what I just did. Just do head and July temperature df, and this is then going to give you just a few columns. So there you go. What you got here is essentially something I didn't mention, and that is because we have 10 layers, each of these layers are now turned into columns. So the values are actually in all these columns. So this is a wide format. We don't want a wide format. We actually want a long format. So we want to have X column, Y column, so we're going to keep them. Then we want all these values to be stored in the third column. And then in the fourth column, we want all these here to be put into a year column. So essentially we'll have then only 4 columns. Okay, the reason why we want that is otherwise gganimate is not going to be able to create a map here. And for ggplot, you would also not be able to straightforwardly create any static map. So in other words, we need to create this July temperature long format. And what we need to do is place this one into a pipe. And then we need from tidyverse a package which is called tidyr. And tidyr has this very convenient function which is called pivot longer. So first of all, what you need to do here is define the columns that you don't want to pivot. So you don't want to transform them. And as we said before, we want to keep X and Y columns as they are. Now, what are the columns that we want to create here? We want to create 2 columns. So all the columns, which in this case is called names2, so all the columns should be transformed into a column which is called year. And then all the values within those columns, denoted here by values 2, should be transformed into a column which is called value. You can also call it, you know, temperature or anything else, but essentially what it does, it denotes values here. Now, once you inspect the first few rows of this data set, you will see that it has only 4 columns, so X, Y, year, and then value in Kelvins. Now, speaking of Kelvins, as I promised you, we'll now get rid of them. But the first thing I want to do is first turn this year column from a character, which you probably noticed in the previous step. Now it's a character, we want that to be an integer. So let's actually first do that. We're simply gonna do that using as integer from base R, and then simply pass here this data frame and also the year as a column name. So that's going to change. Now, the second, I think, even more important thing is to finally create Celsius and just get rid of the Kelvins. So I'm going to create here Celsius. And then Celsius is going to be based on the, of course, the one that we already have. So that's going to be this value. With one exception here, that now to get the Celsius, you need to deduce 273.15 from your Kelvin value, and this is going to then give us Celsius. And then the remaining step is to get rid of this value column because we don't need Kelvins anymore now that we have Celsius. So what we can do is work again on the same data set and simply use here July temperature long, put it into a pipe, and then in this one we can use dplyr from tidyverse and the option select. And we want to get rid of the value, keep everything else. So you can just put here minus value. This is gonna get rid of it. We're slowly but surely transitioning to the stage where we will be creating our first animated map. And to do that, we need some preparatory work. One of that is we want to define here the limits of our data as well as the breaks. Limits are very important when you're animating because you want to include the minimum and maximum values from the beginning to the start so that your legend does not shift all the time with the change of the frames. And this is what we're going to be doing first. So first we're going to define the minimum value here. And the minimum value is, of course, based on this newly created Celsius column, as well as the maximum value. So that's why I'm simply copying and pasting it here and simply changing here from minimum to maximum. So once you have that, we can go ahead and define breaks. I know that at the beginning I did not include into Pacman, but we'll be using here class int package. So you can actually, if you don't have class int, you can add it to the Pacman at the very beginning and then install it. So I already have it here, and I can use class intervals from this package, which is going to help me define natural intervals based on my data. And I can call this actually breaks. Now, what I need to define here is, first of all, what is the column for which I want to create these breaks? Of course, that one is the Celsius column, which we previously created. Then the question is, okay, how many breaks do you want? I'm going to go ahead and have 14 because over here we're going to have both the positive and the negative values. And I want to have a bit of a balance there. And speaking of balance, you can also choose what is going to be the style of your breaks. What is going to be the way of defining them? And there are many ways to define, but I'm going to go here for the equal breaks. Maybe you want to go for quantiles or Jenks breaks or maybe pretty breaks. I'm just going to go here for the equal because this is going to also give me equally spaced legend in the map. Now, the last thing here is this returns a list, but you want only this breaks element of the list, which is going to give you a vector of these values. Two other very important parts of creating maps, in my view, are colors or color palettes and the theme for your plots. So in terms of the colors, what I usually do is I use HCl colors from base R, which helps me actually access a very rich palette of different colors, both continuous and divergent. So in this tutorial, because we're dealing here with temperature which can be cold, so sub-zero, but it can also be warm, so above zero, we want a palette that is divergent and potentially has something like, blue for cold, sub-zero temperatures, and warmer, let's say red and orange for those that are above zero. So first thing, what you want to do here is define how many colors you want. And the best way to do this is simply say, what is the length of the vector of my breaks? So in other words, what is the number of elements of my breaks? So if my break has 14 elements, then this is how many colors I want. So I find it's the best way to kind of go about defining how many colors you need. The second thing, palette. I'm going to go here for spectral palette. Usually I find this palette is used to make temperature maps. And I'm also going to go for it. I noticed Eurostat, for example, is using the blue-red palette. That one is also pretty cool. I'm going to go for this one. You can also check there are some other ones. I would also warmly recommend Temps palette from this HCl colors. and aroma palette. And you can also play with them and see whether they work for you. Now, one more thing, we need to reverse here the palette, because the palette that we get by running without this is with reverse colors. So the blue goes for those above zero and red goes for those sub-zero temperatures. So here we are just simply reversing that. Okay, once this is done, you want to also define the theme of your map. So this is basically what is going to be the design of the map itself. Title of the plot, legend text, legend position, and those kind of things. Now, what I like to do is I like to define here a function, and I call it theme for the win. And within this function, then what I do is define these different parameters. What I like to start with is theme void, which actually gets rid of any excess material around it. For some of you, maybe this is not an ideal function, because it also gets rid of all those breaks, so it doesn't show anymore what is the longitude and latitude values. But I like the minimal design, so I go for this theme void. But this is not enough, because I want usually to specify some other things. So then I also define this theme as well. And then within this theme, I can do several things. I can define, for example, what is going to be my legend position. So where is going to be the legend in my plot? And usually I put it in the top or the bottom part of the plot, so you can also do like this. In this case, I'm just going to put it on the bottom side of the plot. Then you can define also text that is going to appear, in your plots. And one of that is, for example, legend title. So you can define here, how big is your legend title going to be. Important thing to remember, because here we're dealing with text, you need to tell ggplot2 that this is text. So that's why you'll be using here element text. You will open the brackets, and then within brackets, you're going to define the parameters of your text. Now, important thing here is size. Size is really dependent on how big your plot is going to be. Because our animation is going to be 1200 by 1200 pixels, we want the size of the legend title also to be bigger. So I'm going to go for 50 pixels. If you find this too big in your case, feel free to simply reduce this, or if you find it too small, you can also increase it. Now for the color, I'm not going to go flashy about this. I'm just going to go and choose charcoal gray in this case. What we define for the legend title, we can also do for any other text that is going to appear in our plot. And one of that is the legend labels, or in this case, it's called legend text. So I'm going to go for something smaller, like for example, 30 pixels here. Apart from this, you can also define other things, like for example, one of them is plot title. Plot title, this is the place where we're going to be explaining, okay, what is this plot about? So I want this to be a bit bigger. I want it to be, for example, 60 pixels. We can go for this charcoal gray. We will be shrinking a bit the space around this plot. So one thing you want to do is move it a bit towards the map, so downwards. And to do that, you need to put here a negative value. So 0 would mean that it just stays where it is, but I want to move it a bit towards the map. And one thing I also want to have is I want to have this title centered. So that's why I'm putting here that HJust, or horizontal justification, is 0.5. But this is not all. We also want to have a subtitle. Subtitle is going to be the number of the year, and this is something that is going to shift with the animation. Now, I want this to be a bit pronounced, so I'm not going to stick with this, charcoal gray here that we have. I'm going to go ahead and use a bit of a different color, something more kind of going towards red or orange, something that is going to be visible. So I actually opted for this. It's more like a peach color. And I also opted for a bit larger font so that you can clearly see the year as it gets animated, all right? Now, this is almost everything. Last but not least, one thing I really like to add to my plots is the margin. I like to shrink the space around the plot. So get rid of this excess, white space. And what you need to do that thing is define here for each parts of your plot. So for the top side, then for the right side, you want to put it to 0, right? So top, right, left also 0, and then also bottom you want that to be 0 as well. If you want to shrink further, you can then devise here also, negative values. That's also totally fine, but you need to define here what you're going to use. I'm going to use, for example, in this case, just lines. All right, so we have all the ingredients to start making the map, and we can now call to rescue ggplot2. So first of all, I'm going to create object called July map, and then I'm going to call ggplot2, and then I'm going to define one and only layer that we're going to have here. That's the raster layer. So I'm going to be using geom raster, and then we're going to be passing, of course, the July temperature df data, or actually long one. And then in the main aesthetics, we need to pass three things. So the x, the y value, and of course, what is going to be how are we going to fill those pixels? We're going to fill the pixels, of course, using Celsius. So this is the first thing that we need to do. The other things that are kind of now coming to our plate are mostly about customization. And one of the things that you want to customize is definitely, how the legend is going to look like, what are the colors that I'm going to apply. And for that purpose, you can use scale fill and then continuous or something else. I use here gradient. And the reason why we're using for the continuous values in this gradient and as well is because Celsius are also continuous value. So one thing that you can do is define here the title of the legend. So I can, for example, put here Celsius degree. Then you want to define the colors. So the colors are going to be simply that cols factor that we already defined. Then I definitely want to have the limits here. So you remember we defined the limits at the very beginning, where we have the maximum and the minimum Celsius values. Then we want to define the breaks. Breaks we also have. Now, one thing that is important is our breaks have decimal values, and we don't want the labels to also have. So what we're going to do is we're going to round those breaks to the 0 decimal values. Now, once you define this, you can go ahead and customize your legend even more. And to customize your legend, you can use guides function from ggplot2. Because we are here interested in this fill aesthetics, we need to define it here as well. And because we want to have a legend, which is for the continuous legend, we need to choose here guide color bar. Very important. Now, in terms of the parameters here that you can define, there are several of them. One of them is, for example, do you want to have a vertical or horizontal legends? And I would like to have a horizontally oriented legend. So that's the direction. Then you can define, okay, so what is going to be the height of my legend, for example? Here you can define using units. So in this case, for example, because our legend is horizontal, I would like it to be thin. So that means I'm going to go for something like, let's say, 1 centimeter. You might think that's actually quite a lot, but because again, the resolution is going to be also pretty high, we need to also make sure that these values are also high. We already reflected that in the size of the text, if you remember. Now, what we did for the bar heights of our legend, we can also go and do the same for the bar width. So we just simply need to replace here. And now for the width, because it's a horizontal legend, the width needs to be much longer. So I'm going to go here and define, for example, 30 centimeters. Then you can go and, I don't know, define some other things. For example, what is going to be my title position? Where, for example, the title position can be on the top. That makes sense. You can also define, okay, what is my label position in this case? Well, label can be on the bottom, so just below these legend keys. Then, there are some other things that you can also define. How is my title going to be positioned, for example? So what is going to be its horizontal justification in other ways? You can, for example, use 0.5. So it's going to be, centered. What you did here for the title, you can do also for the labels. So you can simply use label, adjust, simply copy and paste, because we're doing more or less the same thing, but just here for the legends names or labels. And then you can also define here how many rows you want. And very important also, I think, by row equals true. You want all of these legend keys to be clustered to each other. Okay, one of the things that you can optionally do here is define your coordinates reference system if you're using something else. So remember, we transformed this. So I do want this to be also reflected in ggplot2. So I want this coordinates reference system to take place. That's, for us, that's important. One of the final things is labs. It's quite important, actually. Title is important because it tells us what actually are we gonna present here. And I'm just gonna go and choose one of the titles I have here, and that is, I'm gonna call this Average July Temperature 2014 to 2023. Now it comes the second part. So this is the part where we define what is going to be, what is going to be showing as the frames are changing. So this relates to years. For the subtitle, because we are animating here, it has a specific format. So it has these curly brackets, which are put under these double quotation marks. So essentially it's defined the same way as title, but everything goes within these curly brackets. These curly brackets, you can see them as a function call, something that calls you to be executed. In our case, it tells ggplot2 that this is actually a place where I want to define how this text changes with each frame. Now, because we're going to be using gganimate and specifically to animate change over time or transition over time, this needs to have this generic name, which is called frame time. So this is not a variable in my dataset or in your dataset. This is simply a call to a generic function, and ggplot will understand what it means. And it means that for every frame, I'm going to change the time label, in this case here. In our case, however, what we have is our year is not rounded. So year has also decimal spots. We want to eliminate that. So the first thing you want to do here is make sure, define this, that it's a numeric or integer variable. That's very important. Second thing, round everything up to the 0 decimal spaces. So once this is actually executed, once we have all the code and this is executed, you get actually, what you get is, you get only the year without the decimal space. And then once this is defined, you can go ahead and also add this theme for the wind, but make sure you have also the brackets, because this is then going to call the function. Now, this is going to simply create a static map, and this is not good for you if you want to create a time-lapse map, which is what we want to do. We need to add here a part which originates from gganimate, which is actually going to tell ggplot2 this is not a simple static map. This is a collection of static maps that I want to animate. So for this, what we're going to do is we're going to create a new object, which is going to be called time-lapse July map. And this one is going to build on top of this July map that we created here, over there. Now, with one difference being that over here, we're going to add a part from gganimate, which is going to add this animation part to it. And this part is called transition time. Okay, within transition time, this is where you need to define what is the variable from the data frame that you're going to be using for time transition. And as we said, we want to have year. Year is already defined as an integer. We don't need to do anything about it. It's already rounded in the previous part of the code. And then the last part here is what is the way you want to animate? So what are the potential ways? And here I like actually to use for this one, which is called ease aesthetics. So how much you're going to actually make smoother these aesthetics. I like to use the linear interpolation here. And also a very cool thing that you can define is how fast this is going to be. So if I choose, for example, 0.1, it's going to be a bit faster. Now, of course, in the next step, you need to account for this by using more frames. So it's either this is going to be smaller, but fewer frames, or it's going to be vice versa, exactly what we're doing here. Now, now we have these two chunks of code, and at this stage you can actually run this whole thing, starting from the definition of the static maps and this. But this is still not going to animate. This is what we're going to be doing in the next step. As I said, for the animation, what we need to do is we need to take this time-lapse July map, and then we need to apply from gganimate a function which is called Animate. So pretty easy to understand. Now, to do that, what we need to do is create again a separate object. I'm just going to call it animated July map. And then after that, what I'm going to do is I'm going to define a set of parameters. Now, one of them is number of frames. As I said before, I want a bit higher number of frames. I'm going to put here 100. So I'm pushing the limit there because I want a bit smoother animation. The second is I want to define also duration in terms of seconds. Now, keep in mind, we have 10 years. We want some, time for each of them. And I'm going to say, let's say, for example, 2 seconds per each. So that would be 20 seconds in total. So that would be our duration. Now, at the very beginning, I want to have a bit of a pause so that it doesn't immediately, start animating and moving frames. And then you get confused, what's going on. As well as the end break. And the end break, I want to make it a bit longer. So I want to actually freeze the last frame so that you can see, okay, so this is for the last year. This is what's going on for, July 2023, because it's the most recent and you might be more interested in that than, let's say, July 2014. As we said, we will define here height with 1200 pixels. We're going to also do the width, 1200 pixels. You can play with this one, see what works for you. We're going to tell gganimate that these are pixel values because if we leave as inches, it's not going to render. It's just, too huge. And then we can also choose here what is the renderer. So within gganimate, there is KrigR, which is the fastest render possible. And I will use it here. And I'm also going to tell KrigR to render in such a way that it creates a loop. In a sense that, once the last frame is done, it starts again with the first one. And then the very last step is after you do this animation, and this should not take longer than, I think, 20 seconds or something like that. The last thing is to save this locally. Because if you don't do this step, it's not going to happen. It's simply going to render, if possible, in your text editor. So you need to take here a function from gganimate, which is called animsave, essentially saving your animation locally. And then we can call it in a certain way. So I'm going to call it July temperature, and important here with the extension, which is GIF. And then the last step here that you want to do is simply copy this name of that animated object that you want to save locally. All right, and here is our final map of every July temperature for the period 2014-2023, from which you can see, first of all, how it changes. Its pulse is almost like a heart with colors changing from the north to the south, becoming cooler or warmer from every year. So there is quite a variation in the last 10 years when it comes to these average July temperatures. You can also see, based on our legend, that the range is pretty high here. It goes from only 1 Celsius degrees, wow, in July, to all the way to 25, but it doesn't go over that. Again, these are the average monthly temperatures. Sometimes you might be interested in the seasonal variation of temperatures. For example, you would like to know what is the specific temperature for spring or autumn throughout the years. And this is what I'm going to show you in this section. So how you can actually do data wrangling for the raster and get the aggregated temperature values for specific season. And then how do you actually also can create an animated map using this newly created raster. So for the seasonal aggregation, we're going to be working with summer. So I will show you how you can aggregate temperature for summer of each of these years. So again, we're going to end up with the same number of layers, but this time, each of these layers is going to be for the summer months of June, July, and August, but again, aggregated. Let me show you what I mean. So first of all, let's define what are the summer months. So the summer months, And here we need to use actually, we need to use strings, of course, but we should define them as the numbers within the strings. So first of all, we consider summer to be June, July, so 06, 07, and August, which is 08. So these are going to be the summer months. Now, the next thing what we want to do is we want to extract dates from our main object temperature predicted. So to do that, we can use a function from Terra, which is called time. So within this function, what you want to do is just simply pass here temperature predicted. Okay. And then this is going to store all of them. Now, the second thing is we want to filter only summer months. So we're not interested in anything else. So we can actually create here an object called summer layers. And what we're going to do within the summer layers object is we're going to use which is going to allow us to actually pick what we need. And then we're going to format here. So we're going to format the dates that we fetched from this one. We're going to format them in such a way that they only show us months. The reason why we're doing that is that then we want to use the summer months filter and select only layers that have these, of course. So once you actually have this, then you can say that from dates that have all these months, I want to select only those that are in summer months that we just defined. All right? So these are the summer layers. Now, if we actually run this whole thing, what we should be able to see when we open summer layers are only those that pertain to summer. Now, this is a bit confusing. It gives you only the numbers here, but you essentially would like to see here if this is correct. But you can actually gauge based on this that it is correct, because if the first months are 6, 7, and 8 for the first layer, then every next one is going to be, for every next year, it's going to be 12 months later, right? So then the June will become 18, the July from this first layer is going to become 19, and August from the first layer is going to become 20. And then every next one adds 12 to that one. So this means that we indeed did fetch the appropriate months. Now, the question that we fetched, after we fetched, is how do we actually aggregate, but only for those months and for specific years? So it's a bit more complicated than aggregating for July months. It was straightforward there because it was simply a month per year. Now we actually have 3 months, which we want to group into one season and then have it by year. But this is not that difficult if you actually follow the next steps. And these steps are the following. So first of all, what you want to do is format these dates in such a way that you have a year there. Okay, so to do that, what we need next is we need to define specifically the names of this summer or this season factor, I would call it. So I'm just going to call it season factor or summer factor or whatever. This is going to be something we're going to use to define then the names of these new layers. Okay, so the season factor is not going to be anything else than simply gluing together some values. So we're going to be gluing year for only the summer layers. So this is where we're going to be excluding the rest. And we're going to be just adding here, for example, summer, so that we know what's going on. And then maybe this kind of underscore just between this year and this name summer. Now, the final part of this whole process is doing the aggregation. In Terra itself, there is a very convenient function when you want to aggregate specific layers that are then indexed in your raster file. And that function is called tap function. That function accepts several arguments. First of all, it accepts, okay, what is your raster layer? The second argument, it accepts what is your index. So in our case, this is that summer layer that we previously defined, so those numbers of the layers. Then we want to give it some kind of a name. So we're going to give the season factor. Season factor and summer layers have the same number of elements. It's just that the season factor is kind of more intelligible. It tells us, okay, this is the year and it's summer. Okay. And then what you also want to do is define here the function that you're going to be using, the aggregation function. And in this case, we want to average. So we're going to be using mean. And finally, we want to get rid of some of these missing values. Once this is done, what we want to do is, and once we actually run everything, what we want to do is the following. We want to get rid of the names of the summer temperature and replace them with something kind of a more intelligible. So currently, if I just check these summer temperatures, you can see, okay, I have here 10, which is expected. So we aggregated. For each year, you have a summer average temperatures. But what we can do is what we did also for July, we can simply here say, okay, I want for these names, I want them to have years. And then once you actually rerun that and see here what we're going to have, we're going to end up with the same layer names as we had for July. So ranging from 2014 to 2023. So once you have this data, you can go back to the steps 7 to 12 and simply plug in this data set that we created, the summer temperature, and it's going to do the same thing for you as it did for the previous one. Finally, I want to show you how you can calculate and then map temperature anomaly. Let's say, for example, we're interested in how much is the average temperature for 2023 different from the average temperature for the period 2014 to 2022. Here's how we can do that. First of all, what I'm going to do is use this base data set that we had from the beginning and then actually convert immediately to the Celsius so that we don't need to worry about that. So I'm going to use 273.15 and just deduce from this. Okay, so that's the first thing. The second is I want to create two raster files here. The first one is going to be the aggregated values, temperature values for the period 2014-2022, and the other one is going to be aggregated temperature values only for 2023. So let's create the first object, which is covering that period between 2014 and 2022. Again, we'll be using subset from Terra to only take those layers that belong to this period. So how do we do that? We can again call to rescue grepl. And from grepl, what you can say is, I put this exclamation mark here, meaning I don't want to include. So I want to filter out. I want to filter out all those names of these layers where the pattern is 2023. And again, here I need to put that I'm interested in the names in this specific temperature predicted raster file. But that is not all. This is simply going to give us all those months for this period. What I want is I want to aggregate them. And here comes to rescue another very cool function from the Terra package, which is called app. This function simply is going to go and aggregate using the function that you define. And here we want average value, so I'm going to use the mean. And again, I'm going to be removing any missing values in this process. Everything that we did here for this period, we can also do for 2023. So I'm just going to go and copy this and paste here and simply change here the names. That's the first thing, to 2023. Then I'm going to get rid of this exclamation mark because I want to get all the layers that have 2023. And then I'm going to aggregate them just like I did in this part. The last part that you want to do to get the temperature anomaly is simply deduce from this first one. So actually deduce from the 2023. So this one, deduce the temperature for this period over here, 2014 to 2022. And this is going to give you what is actually the anomaly in Celsius. So once you have that, you can again go through this entire process of creating the data frame. So I'm just going to go and copy and paste here this. So first of all, we're going to go and turn this into a data frame. Once this is done, then we're going to just simply assign to the last column value name. So as we did also in those previous steps when we were creating this animated map for the July temperatures, then we're going to go ahead and define the minimum and maximum values here for the plots. It's not really needed because we're not going to be creating a time-lapse map. We're going to be creating a static map, but still, it's not bad to do that. Then for the breaks, actually, we first of all, need to define how many we want. So let's say 14 as we did before. That's totally fine. Then we can go ahead and use the same style, which is equal. Just make sure that here you define the proper data frame and the column name. In terms of the colors, we're going to be using again spectral, and again the same arguments as we did in the previous step with defining the colors. We don't need to define the theme, which we already have. So what we're actually going to do is we're going to go back to that very first plot where we were defining, so these July maps. So that would be step number 11. I'm just going to go and copy this part that ends with theme for the win. And then I'm going to go back and customize it a bit. So first things first, we can change the name of this one and we can call it temperature anomaly map, because this is exactly what it's going to be showing. The second thing is we're going to need different data frame, which is temperature anomaly DF. Then for the fill, we don't need Celsius, but we need value. This is not simply Celsius degree, this is Celsius degree difference between these two. Then for the colors, now this is very important. So we have the colors, but we actually want to give a bit more space we want to actually assign warmer colors to everything that is more than 0, and everything that is below 0 or around 0, we can give it maybe blue color. So we need to actually multiply this one. And to do that, you can use color ramp palette. So we can pass calls to this color ramp palette. And once you actually do that, the next step that you need to do is you need to introduce a bit of a bias here towards the higher end. We can introduce the bias 2. So this is going to bias towards those warmer colors, because based on the data, we expect that there's way more increase in the temperature in 2023 compared to this previous period. And then what is important here at the end is how many new values you're going to create. Well, we don't want many new values. So I'm just going to say here, I want the number of values corresponding to the already number of colors that we have. So simply, I'm just going to introduce some new colors biased towards that higher end of warmer colors, and then remove those that were before that were blue. Now, everything else here can stay more or less the same. So this goes for limits, breaks, and labels. Going to the guides, again, there is not much things here that we want to change. In terms of the title, we want to change, of course, that we're not talking about anymore average July temperature, but we are talking about temperature anomaly. And then over here, you can, for example, put 2023 versus that period or something else. It's totally up to you. For the subtitle, we don't really need it because we are not animating this again. So this is actually going to be your code that you can then run for the temperature anomaly map. And then as a last step, you can also save this. I can also show you how you can do that using ggsave. Let me just scroll this up. So let's first of all name somehow this one and put the extension, which is going to be the PNG. Maybe we can call it temperature anomaly. Why not? Then we can choose what is going to be our measure. Again, we are operating with a lot of pixels. I'm going to go for 6000 by 6000. So my width and height are going to be equally 6000 pixels. I also need to tell ggplot2 that these indeed are pixels because by default it takes inches. Then I want to say here that the device we're using is the PNG. Very important here, background, you want it to be white and not transparent. So please include here this argument PNG. And finally, what is the name of the object that you want to save? In our case, that is the temperature anomaly map. And in this final temperature anomaly map, you can see that we have the values from 0.3 to 1.9. So essentially, in 2023, the temperature has increased across Switzerland compared to the average temperature 2014 to 2022. So you could introduce even a higher than bias in the color palette, given this fact. But I also like it this way because it does allow for those values that are closer to 0 to be painted in this blue and green and closer to yellow, and then increasing then from somewhere 0.7 it goes to 1.9 and then becomes warmer and warmer. Alright guys, this is how you can leverage the awesome KrigR package to download Era 5 climate data, do some kriging, and then create some awesome time-lapse and static maps. I'm really looking forward to your own applications and how you take this tutorial on a journey across the world. Let me know in the comment section below how it went for you. If you're new to R and you seek to expand your data visualization and geospatial knowledge in R, I prepared a few cool tutorials for you, so do check them out. See you next time.